explain perhaps the physics of the equation that we got just before the break. The final equation that we got has on this left-hand side the behavior of the gases in the chamber. And essentially this behavior is represented by the time derivative of the pressure. So you assume that the pressure is uniform in the chamber. It is true, the pressure in the low frequency range doesn't change spatially. Next, on the right-hand side, you have the effect due to this time lag. The fact that the time lag itself is sensitive to the conditions, and specifically here to the pressure. And this is expressed according to the STL theory through an interaction index, and the time lag itself intervenes in this expression. Then it is possible that the dynamics can be modified because the injection may itself respond to what happens in the chamber. For example, if you have an injector and you increase the pressure in front of the injector, and if the impedance of that injector is not very large, well, the flow rate will be diminished. So that can be expressed. It can be expressed here. And this happens with the time lag. What you inject at t minus tau is what you burn at time t. And then you have the effect of the nozzle. The nozzle, the gases escape. And of course, this nozzle, if you increase the pressure, the mass flow rate is proportional to the pressure divided by the square root of Tg. So basically, this will be this will increase. So this is the equation that we got. You see the physics of it is it's a balance of mass because we assume that the temperature of the gases is constant. You don't need any other balance here. And we were able to calculate, to determine the stability of this system, what we call this low frequency instability of this system. It's a rocket engine, but the same ideas can be utilized for other systems, systems which look somewhat like a rocket. And usually you have a combustor, you have reactants getting into the combustor. There is a certain residence time. If the residence time is too short, it's not good. If it's too long, it's not good. So you have a certain residence time. And then you have the problem of vaporization and so on. And all this is more or less represented, but of course, somewhat empirically. It's through this interaction index and through this time lag. And of course, the problem is, what is the time lag? What is the interaction index? But it gives you a nice idea of this low frequency instabilities. All right, so now we take a new topic, which is, we have already touched on it a few times. It's perturbed flames. What we are going to do is to look at experiments on conical flames, those very simple flames. We start with something very simple, Bunsen flames. And then we will look at problems of mutual interactions between flame sheets. This is important. When two flame sheets get together, they interact, and this is one of the mechanisms producing very large changes in flame surface. We will represent these dynamics using the G equation. Somebody asked me about that, but we will actually work with the G equation. And we will introduce flame transfer concepts, flame transfer function concepts, and also look at the effects of equivalence ratio perturbations. So the idea is, again, to try to look at this loop. We did a lot on the acoustics. We did less on the flow dynamics and combustion, you see. So we now look at the other side of this loop. To study that, we use this device. We've done some extensive studies of such flames, like this Bunsen flame, stabilized on a burner. You have a loudspeaker at the bottom. I've shown yesterday this film. which I will run while I'm speaking as well. So you know that the flames can interact with the acoustic waves coming from upstream, and depending on the situation, the flames can interact very strongly. This is the M flame or the V flame. The conical flame doesn't produce a very strong interaction. But nevertheless, you will see it does respond to the acoustic waves. But in terms of changes in the area, these changes are lesser than those obtained with the M flame or the V flame. So you can change from one flame to the other. You keep everything else constant by just this magical stick. You know, just put the stick in the flame, and you have a different configuration. And if we suppress the excitation, there is no sound radiation, and the flame is fairly stable here. All right. So one situation which we can also study using calculations. This is an early calculation of a flame in something which looks more or less like a gas turbine combustor. What you see here, you see these flame sheets. This represents the flame sheet. It's a very unstable flame sheet. So what happens here? Yeah. You see what happens is that sometimes pockets are being formed, and these pockets are burning due to this interaction of flame sheets. So this is clearly present in turbulent flames, unstable turbulent flames. And so this interaction between flame sheets is quite of interest. You know, when you separate a pocket of reactants and then this pocket is burning, this will produce a pulse of pressure. We've seen that using, you remember the wave equation, when you have a very strong pressure heat release rate pulse, then it will produce a pressure pulse. So the mechanism is apparent here. You see this, there is a pocket being formed here and burning, and this will produce a pressure fluctuation. So we want to study situations of that kind. The anchoring may also be a problem. We may have velocity disturbances coming from upstream. We may have mixture composition also changing because one wishes to have a constant equivalence ratio. But if the injector responds to the pressure fluctuations, you may have something which is a change in the equivalence ratio, a fluctuation in the equivalence ratio. So we want to study that as well. And also the interaction with boundaries is important. Usually people are interested in the flame, in the mean, and while boundaries are present and interact with the flames. In engines, in car engines, the boundaries are very close. So you have to take care of the boundary. The boundary is very important and not often considered. Most of the turbulent combustion models essentially consider what happens in the mean, in the flow, but at the boundary, the flame still reaches the boundary, comes to the boundary, and this interaction is important. So let's begin with this very simple experiment. So these were experiments at the turn of the century, before the year 2000. We have the loudspeaker, we send acoustic waves here, they get on the flame. You have the flame, which is a conical flame first here. You can study the velocity fluctuation here using laser Doppler. So you have to put some droplets inside this, oil droplets. And then you look at the radiation from the flame using a photomultiplier equipped with a filter. For example, you look at CH star or OH star. And experiments of that kind started very early. For example, Blackshear in 1953. So there is a continuation, but little by little, we got more, better hardware, cameras, photomultipliers, microphones of higher quality, and especially digital data acquisition. That was enormous. When I started working in acoustics, we were actually tape recording in frequency modulation. We had tape recorders with 28 channels, and that was a pretty difficult task. We recorded everything, and then we would bring that to a big computer and do the data processing. Nowadays, you have the computer close to the experiment, you have immediately your result. You just, it took a lot of effort. You had big bands of 28 channels. The recorder itself was weighing perhaps 30 kilograms. Two of us would bring the recorder on the spot. This is how it was, and this is how it is now. So, and what you see now, this is a Schlieren image of the flame as it responds to the acoustic waves. You see, it makes this, we call that a pagoda, or it looks more or less like a pagoda. Now it's moving. You see so these are velocity fluctuations coming here, and the flame responds to these velocity fluctuations. This is the conical flame. This is a 4-color Schlieren, and like that you can see the gradients. So you see that the gradient on this side is the opposite of the gradient of that side. And also the hot gases are here, so it makes a plume. But basically the process that we are interested in is this one. This is at a frequency of 75 Hertz, and the size of this burner is 20 millimeters. So, so for the conical flame, you have a process like that. You go from this, you get to here, there, and you come back, and you have this cycle. And it's always interesting to use dimensionless quantities. What is the dimensionless quantity here? Omega r divided by the laminar burning velocity. And it's also interesting to actually put here the half angle of the flame, cosine alpha 0. And for example, this is omega star is equal to 15. So you can, instead of just using the frequency, you use the reduced frequency. It's better. Another experiment is this one. Now we have the M flame, which is stabilized on the two sides here. And you see that we produce this special shape here. The sheets get closer, and at a point, this torus breaks away, and you have a shedding of this torus of fresh reactants, and it's burning, and you get back to this situation, and it goes on like that. So this is the M flame has this much stronger changes in surface area. The conical flame has some changes in surface area, but not so strong. In the M flame, it's much stronger. Actually, we did all sorts of experiments. Even in one case, you can actually produce cylindrical flames, which are collapsing on the axis here. You see the flame is collapsing, and actually, you know, as the curvature gets larger, very highly curved flames, you have an effect on the burning velocity. And this effect is through the Markstein length or Markstein number. And this experiment here was used to actually measure that effect, because you have a flame which becomes like a cylinder, and you can actually have very high curvature as it collapses. So we studied the V flame, we studied swirling flames. I will tell you about that later. We studied flames interacting with walls. We considered also V flames interacting with the confinement. And I told you that interaction with the boundary can be very important. And this is the M flame and the conical flame. So there is a whole zoology of flames that you can study and you can try to characterize in terms of transfer functions. So one tool in premix combustion is the G equation. So what is this G equation? The idea is that the flame front is very thin, and you can actually consider that it's a surface. In 2 dimensions, it's just a line, and it separates burned gases from fresh gases. So, for example, you have the burned gases here, fresh on this side. And the idea is that the flame is a surface, G of x and t is equal to G0. G is a quantity which goes from 0 to 1. G goes from 0 to 1. So, for example, you can say G is equal to 0 in the fresh stream, G is equal to 1 in the burned stream, and G0 is one of the isosurfaces, for example, 1/2 or something, that characterizes the flame. So what can one say for that? One can say that dG, if we take the derivative of G by dt, this is 0, because G0 is a constant. And this can be made explicit by noting that when you do a total derivative of G, you have to derive with respect to t, and then you have to derive with respect to x. So you have dg by dt plus w. W is dx by dt. It's the velocity of this flame front. And then you have gradient of G is equal to 0. Now, what is the velocity of this flame front? There are two parts in that. One is the flow velocity. So W is the flow velocity. For example, the flame can be transported at a given velocity, v. And then it has its own normal velocity. The flame propagates in the normal direction. It is displaced by a velocity sd, the burning velocity. And so what you can write down is sd times n. And n itself is the normal to the surface, and you know that the unit normal can be obtained from gradient of G. If you take the gradient of, so G is a continuous quantity, but one of the contours, one of the surfaces of G is the flame. And so in this case, if the normal is oriented towards the fresh stream, you see the flame is propagating into the fresh stream like that, this is minus. So now, what is the equation? How does it look like? You take W, so you have dG by dt plus V scalar G plus SD times N scalar grad G is equal to 0. And N here is minus gradient of G divided by the absolute, the modulus of gradient of G.
S sub D is your normal burning velocity?
It's the laminar burning velocity. It's the burning velocity. We call it displacement velocity. So yes. And so let's put this term on the other side of the. So it makes dG by dt plus V gradient of G is equal to SD times the modulus of G, gradient of G. So this is the standard G equation. It's a way to describe a front having a certain velocity. So this is it. And now what we can do is perturb this front, because what we are interested in is not so much the mean, but the fluctuations around the mean. So the idea is to consider the G, and each of these quantities are fluctuating. And to write down an equation which actually tells you about the perturbations. Not, of course, it will contain also something about the mean, but yes.
Just a question regarding the function
G.
a function of x and t is equal to g naught, right? So
Yes.
this is constant. So if this is kind of boundary condition, so I mean x should be specified as a position, right?
No, it's not a boundary condition. It's, you say that the flame is a contour among all these. In the G is a function of x and t, and you consider that the flame is one of the surfaces, the isosurfaces in this. So you say the flame is g of x and t is equal to g0.
So if g0 is a function, not constant, right? G naught is a
Yes.
function or
No, it's constant. It's a constant.
So I'm just
Yes.
oh.
It's a
Maybe
constant.
after
No,
the
you
lecture.
say I'm going to recognize the flame as the place where the function g of x and t is equal to g
So
naught.
we should specify x, right?
No, we don't specify. X is the variable. It's a variable.
So the constant is t.
No, there is no
the-
constant.
the-
No, at each time you have a certain position. You have a flame which is here. This is, for example, a steady flame.
Okay.
What is a steady flame? For example, you have this conical flame. This is steady. G0 is right here. What is the surface itself? It's a cone. It's the surface is in this case a cone, and how is the cone formed? On one side you have the displacement in the normal direction. On the other side you have the velocity of the incoming fresh reactants, V, right here. And you need to have something like that. This triangle will define the cone. You will have as the, alpha is here, alpha 0. So where is alpha? Like that. So alpha 0 is here. Yes, you have this and that, yeah. So as D is here, and V is here, V bar. So what you have is that as D is equal to V bar times sinus alpha 0. As D is equal to V bar sinus alpha 0. This is it. So this gives you, for example, if the velocity v is very large, sinus alpha 0 should be small. Alpha 0 should, you have a cone which will be much longer. On the other hand, if SD is equal to V, sine alpha 0 is equal to 1, and so this makes alpha 0 is equal to pi over 2. So for example, this is difficult to get, but it would be like that. Anyway, so G0 is this one. So here you will have G0 is equal to 0. Here you have G0 is equal to 1. And somewhere you have this, this cone. Okay. So, so now we we plug in all these, we consider that G is equal to G0 plus G1. V is equal to V0, the steady state, plus V1. And SD, we consider that there are fluctuations of the velocity itself, produced, for example, by changes in the equivalence ratio, plus SD1. So you plug in all these quantities in this expression, and this is made in detail in the slides, so I'm going to rely on the slides. And of course, you get the first equation that you get is exactly what I've been doing here. SD0 minus V0 dot N0 is equal to 0. So this is the equation for the steady state. And then you get a transport equation for the perturbed G1 field. So this is the perturbation in the field G. And this gives you an equation which looks like, you have to do all these little calculations, but at the end of it, you get this term. So you see, you get once you use the fact that this is the velocity along the flame. This is the velocity along the flame. It's the, it's the flow velocity parallel to the flame, yes, V0T. And what you see is that the perturbations are transported at this velocity parallel to the flame. And on this side, what you get is the fluctuations of velocities. So what you input as fluctuations will come in here like that. And the other term is SD1 times gradient of G0. So you get these two terms which drive the perturbations along the flame. So this, yeah.
See, now, if that V sub 0T is parallel to the
Yes,
flame
yes,
front,
yes.
then, okay, that's the dot product with G1.
Yes,
The
yes.
dot product with G0
Yes.
should be 0.
Yes, yes,
Okay,
yeah,
got it.
yes, yeah, right.
Dot product with
Yes,
G.
with grad G0,
Okay.
yes. The dot product of V0T with grad G0 will be 0.
Got it.
Yes, yes. Yeah, so this is a very nice little equation for perturbations. It's the G equation. I don't know if you use that, if you have been exposed to the G equation. This is being used, this was proposed essentially by Foreman and Williams around the 1989 or something. The idea is to use contours. It has a number of limitations. It's not, but it's very clean if you want to do theory. And so the perturbed G equation is written here. So you have the perturbations which are convected along the flame at the velocity V0T. So it's the velocity that it has the zero velocity that is along the flame is right here. And then you have the terms which drive that, the velocity V1 and SD1. If the burning velocity is constant, this term disappears and you have just that term. But they look a little bit similar, not quite. You can actually write it in a better form, like this equation in red now. So again, you have on the left-hand side these terms that we discussed, and on the right-hand side, you have V1 times N0 times gradient of G0. And here you have the relative fluctuation of burning velocity multiplied by V0 times N0. So it's like that, effects of equivalence ratio, which are embedded here, and effects of just acoustics, which come in here, look very much similar. So their effects will be through this term here. Burning velocity and velocity perturbations generate disturbances on the flame position in a normal direction, which are then convected along the flame front by the component of the mean local velocity V0T parallel to the mean flame front. So physically, you understand that, but that's the mathematical expression that we can use. And now we go to this flame transfer function. We have already talked about that a few times. The idea, you see, the idea is that we want to represent combustion by considering, for example, fluctuations getting into the flame transformed in fluctuations of heat release. This is described by a function f of omega. It's a description in terms of frequency. We will extend that later on to use what is called the describing function. The transfer function is a linear concept. The describing function is used in control theory. The idea is the following. If the input level becomes large, you have nonlinear effects. So perhaps the transfer function may be a function of the level. So what you get is a family of transfer functions. And if you look at oscillations, the transfer function is good for this linear regime here. When you get to the limit cycle, you need something which is dependent on the amplitude, and this is the describing function. It's a set of transfer functions. We will see that later. All right, so what we do is to try to get, so if we have just this sort of situation with velocity fluctuation here, this will produce changes in the surface area. And we know that these changes in surface area will be reflected in changes in heat release. And we'll do these heat release fluctuations here. If let's assume that phi is equal to constant, this is what we have to calculate using this J equation. If, on the other hand, the mixture is modified, if you have fluctuations in the equivalence ratio, this can be studied. It's not so easy to fabricate that experimentally. We tried, and other people tried. It's not so easy to have an oscillation in the equivalence ratio. You have to engineer something to do this oscillation. But numerically, you can do that. So you can send a wave of equivalence ratio, for example, on this V flame, and you can study how that modifies the V flame. And you can study the heat release that is being produced. That is rather nonlinear. You see, this is heat release fluctuation. These are equivalence ratio fluctuations, and they produce these heat release fluctuations here. And so we studied that with numerical techniques. It's simpler than to do that experimentally. If we want to look at this equivalence ratio changes, this time you have to, on one side, look at flame surface area fluctuations due to velocity, and on the other side, you have to look at what happens because the equivalence ratio is oscillating, and so you will have something like that. So the question is to get these two terms. One is related to this equivalence ratio fluctuations. The other one is related to the velocity fluctuations here. So this was just an initial start on these perturbed flames, and we are going to continue. Unless there are questions. So now we go here. So again, we continue on perturbed flames, and let me just tell you also that there are many other possibilities for flames being perturbed. You have things which are you see you have what is called the Darius-Landau instabilities. Flames, there is no acoustics here, the flow doesn't have any perturbations, and nevertheless the flames develop wrinkles, and you have beautiful experiments of that kind. You have also instabilities which are related to thermodiffusive the Lewis number, sorry, when the Lewis number is different from 1, you may have this very nice wrinkling of the flames. And in general, these growth rates are not very large, but as you increase with pressure, they can become sizable. And it depends also on the compositions and so on. It has some importance. In fact, by getting rid of the Darius-Landau instability, CEFRC was able to get a 10 decibel reduction in welding torch. You know, when you use a welding torch, it produces a lot of noise. Well, much of this noise is produced by the Darius-Landau instability. And you don't need it, in fact. And you can have the same efficiency for the welding torch without this instability. And so by properly, carefully preparing the flow upstream of the welding torch, you can diminish the sound radiation. It has been patented, and you get a welding torch that has the exact efficiency of the others, but with a 10 decibel reduction in noise. So in this case, it's the Darius-Landau instability that you try to eliminate or diminish, and in fact, but we are not going to deal about that. What we are more interested is this interaction with acoustics. We looked at this film at the beginning. You remember in this case, the system is breathing. The flames are interacting, producing pressure waves, and these pressure waves are moving the walls, right, of this combustor. We also want to look at a system of that kind. You know, when you have you are at low equivalence ratio, it's more or less stable, and as you increase the equivalence ratio, you become unstable, and this is unstable. So we've seen that already. So, later on, at the end of this lectures, this is a preview of what we are going to say on Friday, what we are going to see. We work on this annular combustor. In this case, this combustor has 16 injectors, and each injector has the form of a matrix, like that. So that you have laminar, in this case, these are laminar flames that are produced. And so there is a coupling here, not with the longitudinal modes, but with the azimuthal modes. So let's just look at what happens. So one possibility is to have a spinning mode. You see what is seen here at the top. You see the flames become more intense, and this rotates more or less like the speed of sound. This process is taking place. You have to imagine that you have all these flames. These are pseudo colors. These are false colors. It's nicer in red than in blue. And you see that the combustion is spinning here. So this is a spinning azimuthal mode. And then you can have also a standing mode, which is shown below. So this is the response of these flames. But now you see, whoops, it didn't. Let me see. Yeah. So at the bottom, you have a standing mode. You see sometimes all these flames are red, and sometimes these ones, and there is an alter. It goes one way or the other. The first one is spinning. The second one is a standing mode. Yes?
Is there any connection between that spinning mode and spinning detonation?
No, it has a little bit of the same when you have these spinning things, but the spinning detonation goes.
Near the lean limit.
Yes, yeah, it's. There is something shared, yes, there. But here, what is driving this is essentially an acoustic situation where in detonation you have very strong pressure changes. You don't have that here. You may. This may produce up to a few thousand pascals, and one reviewer of one of our papers indicated, but we will never get there in a real system because before that we will shut down the system. But if you are in an aircraft and you say, oh, now the pressure is growing and we are going to shut down the engine, that's bad. So I think it's important nevertheless to study that. We were very happy to have very strong instabilities, 5,000 pascals. That's big, it's very loud. You can hear that everywhere. So, and the effects of these very large oscillations is that some flames can be extinguished. I will show that later on Friday. You can extinguish flames because of very large pulsations. You can also get flashback. Somebody in the room was telling me that this is a problem in their device. They have flames flashing back, going into the injector. You don't want that. So this is why we study that. So we want to study this phenomena. And of course, if you know the transfer function of the flame, this is an initial knowledge that is needed. If you don't know that transfer function, how do you cope with that? It's so basically we need this transfer function. We started I was telling you, yes, on one side you have the transfer function which is related to the wrinkling produced by velocity fluctuations. And on the other side we have this the transfer function that is related to equivalence ratio perturbations. The idea is as follows. In 1998, but this is also exists before that, Leuven and Zinn were explaining the following. Suppose you have a flame here. You have a certain distance. You have a distance to the injector. Let's assume that you have a pressure oscillation at the flame. There will be a pressure oscillation at the fuel injector with a certain lag here. And the equivalence ratio itself might be affected if the manifold responds to the pressure fluctuation that it sees. So the equivalence ratio will be like that. And this equivalence ratio at the injector is convected to the flame, and there is a certain convective delay here. And then there is some combustion delay, and if the three of these delays are in a certain band, that is an odd multiple of the period to the half, then you may have instability. So one mechanism that can take place in gas turbines, which are operating in the premixed mode, is this one. You produce pressure oscillations, they modify the injection of fuel. This produces equivalence ratio perturbations, which themselves are convected to the flame, and as they arrive on the flame, they produce heat release fluctuations. And if these two are in phase, then you have this Rayleigh criterion, and if you do the analysis, you see that the time lag has to be in this range to obtain instability. So again, you see it's a matter of time lag, and it's a matter of having a phase close to zero between the pressure and the heat release. So it's important to look at the equivalence ratio. And I told you it's not too easy to imagine experiments where the equivalence ratio can be varied. We've worked on that, but it's more difficult. But numerically, you can do it. So with Anlor-Birbeau, for example, we calculated a conical flame. You see here you have a conical flame and you send fluctuations in the equivalence ratio. And this is the velocity that comes out of this process. So what is seen here, you see, let's play that again. You see that it looks very much like velocity fluctuations. In fact, what happens is that as these waves impinge on the flame, of course, the normal velocity is changed, but at the same time, you modify the velocity of the gases upstream of the flame. So you get a combination when you do perturbation in equivalence ratio. Well, it produces perturbations in the velocity upstream of the flame. And the two of them then give this shape of the conical flame, which is now like that. So it's this process is a little more complex. It's not just equivalence ratio operating. They have an effect on the flow field, and the flow field itself is modified. So numerically, it's rather easy. Experimentally, it's pretty difficult. So we don't have the same capacity experimentally, but it's a challenge. You can try to imagine. There may be experiments that I don't know of that show this sort of phenomena. I told you we were also looking at V flames impinged by equivalence ratio fluctuations. So anyway, again, what we want to do is to get these two terms. One is due to the fluctuations in equivalence ratio. The other one is due to the velocity fluctuations. And like that, you have the heat release rate fluctuations, and you can get the two components of the two transfer functions, one for each. There is this is done a little bit here. We take care of the fuel mass rate of burning fluctuations due to the equivalence ratio. You find out that this term here will change because of all these quantities. So you change the mass fraction of fuel, you change the burning velocity, and there is a little change in the density. This is not very important, but basically when you change the equivalence ratio, this will change, this one will change, and this one is the most important term. You get that by looking at the curve of the burning velocity with respect to the equivalence ratio. Typically, there is a good slope here. So typically, you get 2.3, for example, for methane at 0.8. So this term is important. This term is not so important. And what you get is basically that an expression of this kind. So you integrate the equivalence ratio perturbations over the surface of the flame. You have this parameter m, which comes in, which looks like 1 plus a being just a quantity that you know. And this can tell you finally what the effect of the of equivalence ratio perturbations, what they develop. We do not consider the changes associated with the curvature, you know, the Markstein lengths, and this term, let's consider that it's negligible. But however, we consider here the changes in SD because there is a good slope here. When you change the equivalence ratio, you change the burning velocity to a good extent. So once we have that, we can actually write this response. And a lot of work has been done on that. The problem has been studied by a number of people experimentally and numerically and analytically. This is Gonyem, who made a nice paper in '96. We took that back, and in fact, there are all these articles and many more. So there's the list of people having worked on this equation and using that to get the transfer function is big, and also there are measurements of the transfer function, and we've done many of these measurements. So again, the G equation, I've presented that. We've seen that before. We looked at finally, how does that equation look like? We've seen that, so I'm just passing these slides. And you have, of course, the equation that describes that finally describes the effect of velocity fluctuations and the equivalence ratio fluctuations is this one. So analytically, you start with that equation, and you can get, if you get already the transfer function for velocity, it's not too difficult to get the transfer function for equivalence ratio. This is what comes out when you look at that expression here. You can actually, these are very close. So the only trouble is that you have to model these velocity fluctuations in front of the flame. You can say, well, I have this nozzle, and the velocity here in front of the flame is just uniform. You have a uniform velocity. And it's not right. The velocity, when you have a fluctuation of velocity here, you produce a convective mode right here, and you have to take that into account. If you do not take that into account, in some early models, like for example in Gonyem, you get a reasonable gain, but the phase is not right. And we've seen that very, very, very well in our studies. So basically, there is a problem of modeling this V1. V1 is not just a uniform velocity. You send an acoustic wave, and that the nozzle, it becomes a convective mode, and this will interact with the flame. So we have to study situations where you have an inclined flame like that, and you impinge on the flame with these velocity perturbations. This can be done. Now, it's just the technical aspects. I'm not going to derive that here. It's a little too complicated. You can look at this paper here, a unified model for the prediction of flame transfer functions, where we do the analysis fully. So basically what you do is you use the G equation in a framework which is this one, XY. The natural framework is to use the inclination of the flame for X, and Y is perpendicular. So you go into this framework, and then you have these are the velocities that are coming in, or the equivalence ratio perturbations that come in. And also you have it is possible that the anchoring of the flame will move. Maybe this anchoring point is not fixed. Maybe it is moving due to the perturbations. So you can take that into account by putting in here perturbations of this anchoring point. So once you've done all that, and it goes through this sort of solution here, actually you can write down a complete solution for an inclined flame, and like that you have two terms, one which is coming from the perturbations, the velocity perturbations that come in, or the equivalence ratio perturbations, and the other one is due to the anchoring point displacement. Let me just show that, again, very early there were experiments of that kind. For example, Peterson and Emmons. Emmons was a very well-known specialist. Later in his life, he worked on fire, but he was Howard Emmons. He was a professor at Harvard. And they did this experiment where they were moving this stabilizer in this direction, and you can see the oscillations of the flame. Boyer and Kina were doing also some experiments like that, and Kornilov in the group of De Goy in the Netherlands has also looked at the anchoring point effects using some electrical techniques. And what I was telling you is that you can also solve the G equation numerically. Again, for the G equation, you have to input a velocity fluctuation. If you put a velocity fluctuation which is uniform everywhere, you do not get this very nice picture. If you put a velocity fluctuation which is a convective mode, then you get something which is very reasonable compared to what you get in the experiment. These are our experiments, and this is our calculations using the G equation. So a numerical solution of the G equation. So definitely you need a proper representation of the velocity fluctuation in front of the flame to get the right answer. You don't get the right answer with a constant velocity perturbation. We also looked, so for example, here you see when I'm saying a convective mode, this is a convective mode here. You see, you have to satisfy, to have the velocity becomes convective. It's not purely uniform in front of the flame. And this is in fact the collection of conical flames. I was telling you that the other day the film was not working, it didn't recognize the film, but this time it does. So you can see how it works. So definitely you see that convection is taking place here. You can see this is the velocity distribution, the axial velocity distribution, and you will see that here that this is being convected. These are just the particles that you see to get PIV, and you see what happens here. Let's see that again. You see it is convected, so you cannot say that the velocity is constant in front of the flame. There is a convection taking place, and you can see it here. This is experimental. So definitely, if you want to represent the behavior of the flame, you have to input something which looks like that. You cannot say V1 cosine omega t. You have to put a convective, and in addition, it's nice to also have the transverse velocity by satisfying the divergence of V1 is equal to 0. So if you want to model such problems, using the G equation, one aspect that is difficult is to represent properly the velocity perturbation that comes on the flame. And the simple idea of saying this is a uniform velocity doesn't work. We can show that, in fact. All right, so now we are almost done. What time is it? Yeah, let's stop at that point. So come back at 11:15, and we will continue and see how these transfer functions look like. So up to now we have just moved around and haven't seen how what they look like.